All right, let's pull back the curtain on one of the most fascinating topics in tech today, neural networks. We hear about them all the time, but we're going to get right into it and demystify how these systems inspired by our own brains, actually learn.
Right from the start, this quote from the source material really hits the nail on the head. The magic here isn't just about being some kind of super fast calculator. Nope. The real power, the whole point, is this incredible ability to learn from experience and, this is the crucial part, to generalize from it.
So that's the big question, right? It sounds like something out of science fiction, but what does it really mean for a machine to learn? Let's get past the buzzwords for a second and actually look at what's going on under the hood.
Okay, first things first, we have to understand the goal of all this learning. And in the world of neural nets, the ultimate prize, the whole reason we do this, is something called generalization. Think about it this way. If you're studying for a test and you just memorize the answers to the practice exam, sure, you'll ace that exam. But what happens when you get a brand new question you've never seen? You're totally stuck. A network that can generalize has actually learned the concepts, so it can tackle new problems. And that, right there, is what makes it so incredibly useful.
So how do you even begin to build a system that can do that? Well, you start small, like incredibly small. We're going to start with the most basic building block of any neural network, a single artificial neuron. Let's meet the perceptron. Okay, don't let the technical terms throw you. A perceptron is basically just a tiny decision-making machine. That's it. It takes in a bunch of different pieces of evidence, it weighs how important each one is, and then it makes a really simple yes or no call. It either fires or it doesn't.
So let's walk through this real quick. Step 1. The neuron gets some inputs, just pieces of data. Step 2. It applies a weight to each of those inputs. Now, you can think of these weights as little tuning knobs for importance. Some inputs just matter more than others, right? And finally, step 3. It adds everything up, and if that total crosses a certain line, boom, it fires. A decision is made. Now, a single neuron, that's a neat trick, but on its own, it's actually pretty limited. And to really get why we need to connect millions of these things together into a network, let's look at a classic problem that one little neuron just can't handle. So here's the fundamental limit. A single perceptron is like a judge who can only draw one single straight line in the sand to separate two groups. If the problem is any more complicated than that, if you can't solve it with one straight line, it's completely out of luck.
And this slide shows the exact kind of problem we're talking about. It's the famous XR problem. Just look at the points. No matter how you try, there's just no way to draw one straight line that separates the 0 answers from the 1 answers. A single neuron is completely stumped. And honestly, this was a huge roadblock in the early days of AI research. So what was the solution? Well, it turned out to be teamwork. By connecting these neurons together in multiple layers, they can work together to draw all sorts of complex, squiggly boundaries to solve problems like XOR and, well, much, much more. But that leads to the next huge question. How do all these connected neurons learn which squiggly line to draw?
So how do these networks actually tune all those little importance knobs, their weights? Well, the most common way is something called supervised learning. And the best way to think about this is like a student learning with a teacher who, already has all the right answers. Here's a quick side-by-side. On the left, with supervised learning, you have a teacher. That's a data set where all the answers are already labeled. The network's job is just to try and match those answers. Now on the right, you have unsupervised learning where there's no teacher at all. It's just given a giant pile of data and told, go find something interesting. We're going to start with the teacher first. So the whole process begins with the network looking at an example. Let's say it's a picture of a cat. It takes in all the pixels and based on its current settings, it makes a guess. It might guess dog, but the teacher, our labeled dataset, knows the correct answer is cat. So now the network can actually compare its guess to the ground truth.
And this right here is the aha moment. The network calculates its error. How wrong was I? The size of that error is the whole key to learning. A really big error means, hey, a big adjustment is needed.
And here comes the really clever part, a process called backpropagation. That error signal gets sent backward through the whole network. It tells every single connection how much it contributed to the mistake. And based on that feedback, each neuron adjusts its little tuning knob just a tiny, tiny bit so that next time the guess is a little closer to cat. You repeat this millions of times, and the network actually learns to see. But what happens when you don't have a teacher? What if all you have is a massive, messy pile of data with 0 labels? This is where unsupervised learning comes into play.
The network's job here isn't about being right. It's about finding something interesting. It's basically a data explorer, sent out to find hidden structures all by itself. And this is so useful for things like, say, clustering millions of customers into natural groups for better recommendations, or helping scientists sift through mountains of climate data to find the most important variables.
A really great example from the source material is something called Principal Components Analysis, or PCA. So imagine you have data with like 100 different features. PCA is an algorithm that can look at all of that and basically say, you know what, out of all these 100 dimensions, these two are the ones that really matter, the ones that capture most of what's going on. It finds the most important patterns without any labels to guide it. Pretty cool.
Okay, so whether it's learning with a teacher or exploring on its own, we have to come back to our main goal, generalization. Because you know what? It's actually very easy for a network to cheat.
And what we're seeing here is the critical difference between really learning something and just memorizing it. Good generalization is a nice, smooth fit. The network has actually captured the real underlying pattern in the data. But poor generalization, what we call overfitting, is when the network just memorizes every single quirk, every bit of noise in the training data. It's just like that student who memorized the practice test. They do perfectly on what they've already seen, but they completely fail on anything new.
So how do you force a network to generalize well? Well, one of the biggest keys is data. Lots and lots of it. A rule of thumb from the research is that you need about 10 times more training examples than you have weights in your network. Now, why so much? Because with tons of diverse examples, the network is forced to learn the true underlying pattern instead of just memorizing the quirks of a small dataset. It can't cheat. These models are data hungry for a very good reason.
And this brings us to our final and kind of provocative question. When a network does really well on data it has never seen before, has it achieved something like genuine understanding? Or is it just an incredibly sophisticated pattern matcher that's found some clever statistical shortcut that we just haven't figured out yet? It's a question researchers are still grappling with, and it really sits at the very heart of what it means for a machine to learn.